Although gravity waves in liquids are easily seen, they're not the most common waves we encounter in fluids. Compressibility waves in gases are certainly more common, since sound waves are compressibility waves. Sound waves are small amplitude compressibility waves. A large amplitude compressibility wave is a shock wave. Compressibility waves move at very high speeds and can usually be seen only with the aid of special optical devices. On rare occasions, if the light is just right, shock waves may be seen with the unaided eye. However, we can easily detect the passage of a compressibility wave by the changes in pressure associated with it. Our ears, for instance, are very sensitive detectors of pressure changes. Indeed, we classify all small amplitude compressibility waves, whether they are audible or not, as sound waves. As a model for a gas, here you see many particles floating in the surface of water, more or less evenly spaced. The number of particles per unit of surface area represents the density. As a compression wave comes along, you can see the particles accelerate in the direction of the wave motion, and you see the density increasing, that is, the particles moving closer together. Much of what we have shown you concerning one-dimensional gravity waves applies equally well to compressibility waves if we simply replace the depth of the fluid h by the density of the fluid rho. In fact, a compressibility wave may be described as a region of increased or decreased density that moves relative to the fluid. Just as depth is proportional to the amount of fluid per unit length in an open channel, so density is proportional to the amount of fluid per unit length in a closed channel. The fluid flowing into this length of open channel increases the depth. The fluid flowing into a length of closed channel increases the density. In a compressibility wave, the pressure depends on the density. Just as in a gravity wave, it depends on the depth. Although surface gravity waves and compressibility waves behave quite similarly, they are propagated by entirely different physical mechanisms. The fluid acceleration in gas waves is due to elastic forces associated with the compressibility of the fluid rather than gravitational forces. The speed of a small amplitude isentropic compressibility wave increases with density, just as the local wave speed of a surface gravity wave increases with depth. This increase of sound speed causes compression waves to steepen. When we say that a compression wave steepens, we mean that the density and velocity gradients increase in the wave. What happens when these gradients become very high? That is, when the wave becomes very thin. The compressibility wave cannot topple over like the surface gravity wave. Instead, the density and velocity gradients reach limiting high values in a thin region and remain constant. By looking from above at only the inflow and outflow of an hydraulic jump, we can gain an impression of the steep velocity gradient. In compressibility waves, these limiting high gradients are determined by the effects of viscosity and heat conduction, which up to this point we have been able to ignore. The reason that viscous forces become significant here is that fluid particles going through a steep wave experience high rates of deformation. Viscous forces are proportional to the rate of strain. Hence, viscous forces become significant in a steep compression wave. The steepening tendency is opposed by the action of viscosity and heat conduction, and a limiting steep wave results, called a shock wave. Stationary shock waves can be produced in a supersonic wind tunnel. Here the gas is moving at supersonic speed ahead of the shock, Mach number greater than 1, and at subsonic speed behind the shock, Mach number less than 1. This is analogous to the stationary hydraulic jump we saw in the flume, with fluid moving at supercritical speed ahead of the jump and subcritical speed behind it. Recall that the total pressure, total head, dropped in going through a hydraulic jump. In the same way, total pressure drops in going through a shock wave, because some of the mechanical energy is changed into internal energy by the dissipative action of viscosity and heat conduction. Unlike the hydraulic jump, a shock wave is extremely thin, on the order of a few mean-free paths thick, about 1/1,000,000th of an inch at room temperature and pressure. A moving shock wave is what you hear when there is an explosion. It is the thunder that accompanies lightning. It is the sonic boom you hear from a supersonic airplane. We can produce moving shock waves in the laboratory in a shock tube like this one. We put high-pressure gas on one side of a frangible diaphragm and low-pressure gas on the other side. The diaphragm is made of celluloid sheet. We break it with a knife like this. So with high-pressure gas on this side and low-pressure gas on this side, when we break the diaphragm, we create a shock wave which moves at supersonic speed down the tube. By pulling a gate in the wave channel, we can produce a positive surge wave. This is analogous to the shock wave in this tube. This end is open, and we have placed streamers here to make the motion of the air visible. Now I will break the diaphragm. You noticed the wind behind the shock wave, just like the drift speed behind a positive surge wave. An atomic blast sends out a spherical shock wave, followed by a strong wind, which is the air moving at the drift speed. We can produce very strong shock waves in this shock tube. The high pressure section is here. The low pressure section is this Pyrex tube. The temperature behind a very strong shock wave can become so high that the gas molecules are torn apart, dissociation, and even electrons stripped off the atoms, ionization. Ionized gases emit light, and hence this phenomenon is easily seen. The diaphragm is located here. This is what a diaphragm looks like before it is broken, and this is what it looks like after it is broken. You can see that we're dealing with very strong pressure forces. We have argon in the low pressure section of the tube. You will see the shock as the argon ionizes. I'm going to turn down the lights. You watch the tube. Now I will break the diaphragm. So far, we have concentrated on one-dimensional waves. Two- and three-dimensional waves involve the same basic concepts, but can become very much more complicated. These remarkable pictures were taken at nearly 400,000 frames per second. This sequence shows a normal shock wave passing over a wedge. Here, a shock wave passes over the sharp edge of a flat plate. Notice the vortices produced at the sharp edges and the great number and variety of shock reflections and interactions. We have shown you some wave phenomena in fluids, chosen to emphasize the basic concepts of wave propagation. First, the local accumulation of mass, which is due to depth changes in the gravity wave and due to density changes in the compressibility wave. And finally, restoring forces, pressure forces, which are due to depth gradient in the gravity wave and to density gradient in the compressibility wave.